taken today with and then with Harley's talk about, how he could look at the same simulated galaxy from different angles and see very different things. And I think it's something we really need to think about, both in terms of how feedback works in terms of making holes for ionizing radiation to get out. And I wanted to show an example here of one particular local galaxy. It's actually the same one, J1044, that Matilda showed earlier. And the pointer here. It's a clumpy little galaxy. This is the UV bright starburst knot that when you do cost spectroscopy, everyone looks at and finds a very young age for the starburst. And when you look at it with IFU data, this is KCWI data from Keck, and this is a map of the ratio of oxygen 3 to oxygen 2. You see that the high, bright, high ionization zone is right around that starburst knot, as you'd expect. And it actually continues up into this region. There's oxygen 3 detected, but no O2. So the point is that there's an ionization cone up here where the galaxy is density bounded, but it happens to be pointed, 90 degrees to our sight line. And there's something I like to call the supernova timing problem, which is that, this burst, the age is only a couple million years. So it's not really old enough to produce most of its supernovae yet. Okay, maybe a few. And in high-resolution HST images, we see some shells starting to form. But it's too young to have a galactic wind. So how is there a hole, right, to get ionizing photons out? And the IFU data beautifully shows, if you map the kinematics, over here is a galactic outflow, a biconical wind of gas moving toward us and away from us. But of course, it's coming from this post-starburst region where the age is 20 to 30 million years old, and there's been times for lots of supernovae. So it's like, if there's leakage from this galaxy, it's a hole that's blown by these stars, but ionizing radiation that's coming from these stars, and they're just interacting over on one side of the galaxy. And I kind of wanted to pose the question and ask, when we're trying to measure Lyman continuum leakage and gain insight from local analogs into what leakage is happening at cosmic dawn, what's the best way to look for that, really? Like, the gold standard, right, has been looking directly for the Lyman continuum, right, at redshifts of a few tenths where you can see it with HST. But you only directly see Lyman continuum if that hole is pointed right at you. And might mapping nebulae, where you can see the ionization structure, actually be a better way to measure Lyman continuum? When you think of the nebula as a calorimeter kind of around the galaxy, that can give you more of a view of what's going out in any direction.
David, I can do that. If the question will presumably be for you.
We're going through a revolution in terms of data from SK in the future, and right now already ALMA. And I think combining these multi-modes of observations will help, because you'll see for this galaxy, if it could detect something, you'll see the distribution of the gas in a way that will give you another whole dimension of what might be really where the holes are. So I don't know, all the people need to tell me what the resolution is, but I would suspect that it might be able to just detect that there's actually a hole on the left and not on the right. And with these observations, UV, you can then see the ionization. So the suggestion is that our teams all around the world collaborate with each other to address Crystal's very interesting question.
Other questions or reactions to the point Crystal made?
So I say this as maximally not an observer, but it seems to me like there are trade-offs. I mean, the advantage of measuring it directly is you've measured it directly. You know how much flux is coming out. The disadvantage is you need a very large sample to integrate over solid angle, right? If you had enough examples, well then, fine. I don't care if I only see it in 5% of cases. I integrate the angle average by brute force, and that's actually the number I care about. The advantage of using the nebula is you are presumably then sensitive to a much larger range of solid angle. I would presume the disadvantage is that actually turning it into a flux is a much harder problem if you're only seeing indirect nebular illumination. I can see advantages of each, but am I getting the trade-offs about right there? Am I way off?
I would agree with what you're saying about sample size for sure. Yeah.
Actually, I don't have an answer of your question. I just wanted to make a comment. I don't know exactly. One of the aim of the study that we are doing on these galaxies using UV imaging is really to map the Lyman alpha, the carbon 4, the carbon 3 to see, like, to try to reply to this question. So maybe in 1 year I would be able to reply to you. But in terms of multi-wavelength data, in theory, like in my recently approved program of ALMA, these galaxies should be there. So if they will observe, we will have also that information, and maybe putting together different like multi-wavelength observations, we could really understand what is going on. So more data.
So I agree with you that the best indicator of Lyman C leakage is to see the Lyman C, but obviously we can't do that at reionization, right? But this is why I've been pushing for the infrared for so long, because at least from the dust perspective, it doesn't matter as much, right? So maybe if we can come up with, I mean, the issue is you can't apply these diagnostics then at redshift greater than 6 because we can only, we have 2 lines with ALMA unless we're lucky and get a nitrogen line, which is very rare. So perhaps it would be a good idea if we can use MIRI or something like this, look at this sort of infrared line, see if those can be used to at least come up with a diagnostic that works on local Lyman C ones and push that to slightly higher redshift where we can see both and at least check. That way in the future maybe we'll be able to get it. But yeah, from a simulations perspective, I can say that, I mean, the simulations have for a very long time said the Lyman continuum leakage is a feedback regulated quantity. Literally everybody agrees on this, and the observations are telling us something completely different. And so I have a feeling this is where the simulators have been wrong for about 20 years. But it's not clear what we can do to do much better because we can't hit the resolutions needed in order to model the problem correctly.
I mean, a related question I've got to ask to you and the other simulators is, do you actually believe that there are any local galaxies that are analogs of kind of the structure of the interstellar medium in leakage? Or is the geometry and the turbulence so different at high redshift that the idea of a local analog is just nuts?
I don't think a local analog is nuts. I think the idea of finding a one-to-one comparison is obviously nuts, but studying the low redshift universe and looking for things like this, I think, is the best place to do it because you cannot do it at high redshift, so we don't have another choice. But what I would say is we just have to be a little bit cautious. I mean, with the first 3 ERO galaxies, we try to look at the statistics of the, nebular emission lines and compare them to the low redshift, blueberries, green peas, whatever your funny named galaxies are. And at least one of them was a wild outlier. The second one was on the edge of the distribution. And so, with much larger samples, things are looking a little bit better. And there are clear analogs of green peas at high redshift. It's just, it's not representative of all of them. And then you have to ask the question, are these the galaxies that reionize the universe? And that's still very much an open question.
And I think this one first before David, if that's okay.
I think the answer to your question from my personal view is that previously we don't have this kind of code and model to deal with the geometries when we develop this kind of diagnostics. And So the struggle with our observers between the densely bounded or relatively bounded cases for high ratio nebula is kind of, because we don't have two. And so what we found or developed based on the 1D model is basically to increase the ionization parameter, so the correlation is more built based on this kind of assumption or this kind of trend. So as to the ISM structures, I don't think we have this kind of things nowadays, even for the high ratio one. And in fact, we are doing something to develop this kind of geometry affected emission line diagnostics and ICFA. But we find that if we change this kind of density field by using different mathematics, and you probably have totally different emission line behaviors. So how to find the most realistic density field is quite the vital key to develop this kind of diagnostics. And I don't think this is also a long-term puzzle for myself there, because the green pea and other galaxies in local doesn't have that kind of highly turbulent ISM as we see, and also the clumpiness as we see at high ratio. So I think maybe we need to have more high spatially resolved simulations to help us to understand this kind of question.
I'm asking this question of the theorists, and that is, when you see a lot of simulations, they look as if they might also, at high redshift, I see that they look to my eye as if they were a part of a complex interaction. So if you model multi-object mergers at low redshift, do you get conditions, turbulence, densities, etc., similar to that which are at high redshift, because that's low mass resolution? But am I totally off to say that maybe some of the merger systems we see at low Z, especially these low mass galaxies, might not be that far off from a high redshift counterpart? I'm asking this as a total innocent ignorant.
Yeah, I think systems might be a good analog to some of the conditions at very high redshift. But I would also guess that even if they're not interacting, low mass galaxies that are particularly compact might be a good place to look, because these Z of 10 galaxies on average are 10 times smaller than the zero galaxies that have the same mass. But I think size is probably critical, because more compact means much denser, and I think that's a critical difference between.
I mean, metallicity is clearly another thing that makes some of the small systems, I think, locally better analogs. We don't understand clearly how that affects some of these very massive stars that may be forming, but it's probably the dominant parameter, even if, and that may be a good segue into some of our next questions about star formation efficiency and things.
So we do have more questions, but I'm not sure what our time limit is. I know we started a little bit late.
Let's take one from Joel.
We can certainly go another 10 minutes or so and not be late for dinner.
We have to have more questions to put up.
Just on that issue, though, that was just discussed, there seems to be a dichotomy between about 100 parsecs across, I mean, really incredibly small, versus other galaxies, similar luminosity, same redshifts, 12 or something like that, which are much bigger, and not much in between. What's going on?
I assume this is a question for the audience as a whole. If volunteers. So, I will repeat. Yeah, so I think Joel pointed out that at very high redshift there appears to be two populations of, like, one that's more compact, about 100 parsecs, and another that's more diffuse, and nothing in between. I'm actually not very familiar with this phenomenology, but I think we have some.
I think you were talking about my plot, but I was comparing mostly to observations prior to JWST. More JWST results find more compact objects. I have to put them in the plot. They're still preliminary. But I was comparing to observations before JWST. But now JWST has the resolution to find more and more compact galaxies, right? So probably that whole region will be filled over the next few years. That's my guess.
We have some other hands raised in the back. If
Yeah, so Claude, in your talk, you showed the very different looking CGM at high redshift. I wanted to ask this question earlier, sorry. And so I'm just curious what kind of column densities that this extended CGM would have in things we might observe, like H1 or if it's multi-phase, O6 or whatever.
So there's a huge range. So for the particular images that I showed, I'm not sure. But with Jonathan Stern, we had a paper, I think in 2021 also, where we showed that in just because the universe is denser at high redshift, the cool gas in these halos could reach DLA columns on CGM scale. Not to say that everything is going to be a DLA, but at these high redshift, I think you can expect a large covering fractions of Lyman limit systems and even DLAs.
I have a response to Joe's question and a question to Claude Andre. So reaction to Joe's question, I think the dichotomy or the diversity of compact and diffuse or normal galaxies is not only in the high-Z phenomenon. In the local universe, it's the same. We have galaxies as compact as M32, 100 parsecs in diameter, right? I don't know the answer. I think it's one of the.
Is there a gap in the distribution? Is this like a bimodal distribution, or is this a distribution
I don't think for
scale?
the local universe is as bimodal as we have seen today for high-Z, but I don't know. I don't know if it's an obvious bimodality there, but it's definitely a. I mean, it's one of the. I would say it's the one of the most persistent challenge to lambda CDM for the small-scale issues. That's we have compact dwarfs that cannot be reproduced in simulations in the local universe. Not only in satellites, even the field galaxies, some of them are very compact. I don't have the name here that on top of my mind, but they're there. But my question is to you and to Avishai, to Zhao and or the people working on SFEs, FFBs, etc. Can we first define SFE first? Are we referring to the macroscopic, the galaxy scale star formation efficiency like m star over m halo, or are we talking about the macroscopic, the Koenig-Smith law coefficient epsilon? And what's the connection between these two? We showed you a plot that that SFE is not evolving elevated at high Z. You are obviously referring to the global one, right? And also I saw Robert's paper, Firebox paper, right? That SFE is defined in a similar way. It's the star formation rate divided by the growth rate, which also shows a marginal redshift trend, Z to the power of 0.1, if I remember correctly. But I think FFBs are referring to the local, micro level SFE, right? What's the link between these two? That's a question to you all.
So while I make a comment, I'll see if there's a volunteer to define FFB. It's not part of our, it's not something we propose. So I don't feel qualified to define it for you. But the related comment that I can make is in, in the fire simulation, we do find on small scale very high efficiency per free fall time. That's part of the prescription. In the dense gas, our dense gas is turning into stars. It's 100% efficiency per free fall time. But the results that kind of I showed in my talk today, and which kind of was studied before in fire, is that this leads to halo or galaxy integrated star formation efficiencies that are similar to the Beruzzi and Moster stellar halo mass function. And in the recent work, what we're showing is that this does not appear to be kind of changing as we go to redshift of 10 to 12. And so we're not noticing the emergence of kind of a new phenomenon. So in that sense, we would say we don't see evidence for FFBs, but it's possible I'm misinterpreting what I should be looking for.
I do want to ask you about the fire simulation, whether you actually do resolve the physical processes that should give you FFB. What is the spatial resolution?
In the dense gas in many of these simulations, it goes down to about 1 parsec. And so we do resolve gas with densities well above 1,000 particles per cubic centimeter. And that gas gets turned into stars with 100% star formation efficiency per free fall time. But only a small fraction of the gas in the halo at any given time is that. Yeah.
My impression is that you need to go sub-parsec for all the processes to work. You need the turbulence injection scale to be resolved inside clusters of 10 parsec. So it should be around 1 parsec or better. You want magnetic fields, cosmic rays, black holes, everything to be resolved on a scale of 1 parsec and more. And that's the question of whether the reason that you don't get very high star formation efficiency is because you cannot get it with the resolution that you have. But maybe if you increase the resolution or improve the subgrid recipes, you may be able to resolve a higher star formation efficiency. I just wonder.
Yeah, so I think this is something we can talk more about. I guess I'm not fully following, because we do have gas that reaches the densities where you predict an FFB, and locally, not an FFB, that's what they call it. And locally, we do see that phenomenon. It's kind of by construction in our simulation, we get 100% star formation efficiency, but it's only kind of applies to a minor fraction of the halo at any given time. So that's why the kind of the time interval is. It is true that we have finite resolution, so it's not necessarily the last word on this, but that's kind of the outcome of the current model.
Yeah.
Mark, do you have a microphone?
Yeah. Yes, I do. So with respect to local efficiency, global efficiency, and observations, I want to link this to one of the points that Harley made in his talk, which is that for the local efficiency, you have observational diagnostics, which are probably not at all related to integrated galaxy scale things, right? So in the local universe, the best evidence we have that you don't ever see really efficient star formation is the HCN to IR ratio. That, HCN is basically telling you about gas at densities of order 10 to the 4 per cubic centimeter. IR is telling you star formation rate. If there were a region where the star formation efficiency were 100%, or even approaching it, the way that should show up is a really, really low HCN to IR ratio, which you never ever see, right? So it's clear in the local universe it never happens. Now, you're not going to observe HCN from a galaxy at redshift, whatever, but maybe you can look at O32, which seems like it's getting its similar physics. The question is, so that'll tell you, do you have the first step? Do you have the local high efficiency? Now, your point is that's maybe a necessary but not a sufficient condition to get a high global efficiency, and that's a separate question. But I think we can see that locally, star formation is never more efficient than 1% per free fall time, based on the diagnostics that are actually telling you about the dense gas. Does that matter for global efficiencies? I mean, I think you guys have argued pretty strongly that it doesn't, and that may well be right.
I may briefly add to Mark's point. So I can't even imagine the like even if you have local 100% star formation efficiency, how can you achieve like a similar level globally? You need to coordinate all your FFB clusters to explode at the same time, right? And you don't have subsequent gas accretion in order to achieve a high global SFE.
And I fully agree with Mark. The local efficiency remains low. There's no problem. In fact, it's degenerate. You can change the local efficiency and you hardly affect the global efficiency. The global efficiency is much more driven by the mass loading factor. And you can change the mass loading factor drastically and get the global efficiency to change a lot with a fixed, pretty low local efficiency. So I fully agree with Mark.
Any other questions or reactions on this topic? That'll be the last opportunity. Okay, well, I think we can talk more about this over banquet. Thank you, everyone.